So the goal for today is short. We're going to just become familiar with vectors, and we want to do a couple of things. First of all, terminology. We're going to spend the entire work working with vectors. We want to make sure that we're all referring to the same parts and terms associated with vectors as well as the notation. Today we're going to take vectors and resolve them or break them up into the vertical and horizontal components, which will be useful for everything else that we do. And we're going to find the resultant of vectors today, which is basically the total or the sum of two vectors. And the last thing before you leave today, I want you to be familiar with the three common forms of a vector and be able to switch between them. You already know the mathematics that's going to be involved with what we're doing today. It's just a matter of applying it. So this is where the little handout that I gave you begins. First of all, we need to distinguish between two different things. Everything that we've done so far, about 15 weeks worth of stuff, we have always worked with scalars. And a scalar is a numeric quantity that only has size. There's no direction. Okay? Many measurements are scalars. Examples of this, 125 pounds. If something has a weight of 125 pounds, it's just 125 pounds. There's no direction associated with it. It's just a quantity. That's it. Or when we measure time, 43 years, that value doesn't have any direction associated with it. What we're going to work with now are quantities that are meaningless unless you know an associated direction. And that's what a vector is. A vector is a value that has magnitude like we've had before, but now we're also going to have a direction. So a vector always consists of two parts. Can you think of things that have to have associated direction with them? Well, of course you can, because I gave you the handout and you see what the slides are in advance. Well, when you're driving in your car, okay, if you say you're driving 60 miles per hour, that's a speed, and a speed has to be in some direction. You can't be going 60 miles per hour and not be going anywhere. So as long as you're going 60 miles per hour, there has to be an associated direction. That makes it a vector. So we would pin to it a direction, 60 miles per hour north. All right? If you watch football, somebody has an 8-yard change. Well, we don't know whether that's good or bad unless we have a direction associated with it. So we would say that an 8-yard gain would be a vector. It has a magnitude of 8 yards and a direction of forward. Does the basic idea make sense? Okay. Well, a little bit of vector notation. Now, I'm going to show you some vectors in a minute, but first of all, I just want to introduce this notation, then we'll look at some examples. First of all, you represent a vector by an arrow. And the arrow indicates the direction, what direction it points is represented by the arrow, and the length represents magnitude. So the longer the arrow, the greater the magnitude. We'll see an example of this in just a minute. Every vector has two parts, logically named the tail, which is the back end, and the tip, which is the forward end. This is important. To distinguish when we're writing out vectors using algebra, we distinguish vectors with bold type, or by putting a little arrow over the top of the letter. That distinguishes that we're talking about a vector instead of just a scalar, which is what all the other variables that we've worked with are so far. I'll show you an example of this in just a minute. And to emphasize that, when you see a bold letter, you have to assume that it's talking about a vector variable or an unknown vector as opposed to simply an unknown number. Now, here's some examples of that. Start out with the vector A. Now, if you look at A has got some magnitude. We don't know what it is, but it's also got some direction. The direction of A is given just like angles are given on the Cartesian plane. It's the same system. So as you look at vector A there, anybody care to give an estimate of what the direction of A would be? First of all, would it be positive or negative angle? Probably. Positive. More or less than 90 degrees? Less. Probably somewhere around 55, 60 degrees, somewhere in there. We don't know. So A would have a direction of around 55 degrees. Now, if you take a look at B, B is pointing in the same direction, so it has the same direction, but it's only got half the magnitude. Now, these vectors can represent a lot of different things. Maybe a vector represents wind speed. A would represent wind that's blowing in the same direction, but twice as strong as B, which is the same direction but half the magnitude. C has the same magnitude as A, that is the same force or same speed, but in exactly the opposite direction. Again, all relative to the Cartesian plane, which is how we'll handle most vectors. It's important to note that a vector doesn't necessarily have to have a location, and typically doesn't have a location. We put it on the Cartesian plane so that the tail is at the origin and the tip points off towards one of the quadrants. But we just do that for the convenience of computation. It doesn't have to be associated. For example, if we say that a car is driving 60 miles per hour north, we don't have to know where that's happening, just that it is happening somewhere. Okay. Polar form. The most simple way to visualize a vector is in polar form, and a vector in polar form gives the magnitude and direction. So for example, if we have the vector 12 at 81 degrees, that means that we're going to have a vector pointing off towards 81 degrees, and it's going to have length 12. That's all there is to it. I won't get fussy and use a protractor here, but it would look approximately like that. Vector 12 at 81 degrees. Okay, or 6.5 at 225 degrees. 0, 90, 180, 225 is going to be down in the third quadrant. The magnitude here is 6.5, so it's going to be just longer than about half the length of that. Again, we're doing rough sketches here. We don't need to be exact, but 6.5 at 225 degrees. And the last one, negative 10 at 120 degrees. Now, we would go towards 120 degrees, which is going to be in quadrant 2, but the magnitude is negative 10. So it's going to point backwards from that. All right? So here would be 120 degrees, but we're going to point backwards from there. So what would be the other name for this? This blue vector, negative 10 at 120 degrees, we could also call exactly. We could call it positive 10, but add 180 degrees to that, and that's going to be 300 degrees. This is the way that we would like to express this vector. We'll find that in the long run, it's typically easier to work with vectors that have positive magnitude. We don't have to, but generally will make the computation a little bit easier. That's one form that we can express a vector in. The advantage is that it's easy to picture. The second form is rectangular form. And rectangular form assumes that a vector is in standard position with a tail at the origin, and we simply give the coordinates of the tip of the vector. We're going to be down in quadrant 3. To the left 4, down 6. Somewhere down there. And we have the vector negative 4, negative 6. Or similarly, we can have the vector 5, 0, which is going to put us where? Right along the positive x-axis. Out 5, to the left 0. And we've got that vector. Now there's a third system that we won't work with very much, but it's worth noting at this point, and that's called the complex form. The good news is that complex form is exactly the same as polar form. It's written in a slightly different way. You will work with complex numbers. If you're in electronics, you'll work with them quite a bit. If you go on and take Tech Math 2, you'll do a lot of computations with complex numbers. We're not going to do any more than recognize that we can take a rectangular, a vector in rectangular form and write it as negative 4 minus 6j. If the first one that we drew here, negative 4, negative 6, could be written as negative 4 minus 6j. And the reason we do that is because when you start working with imaginary numbers, you'll work on what's called the complex plane, which is almost exactly the same as the Cartesian plane, except that this is not referred to as the x-axis. It's called the real axis. That gives you the real number, which is first. The other axis is called your I or j axis. And so this number gives you the real component, and the second number gives you what we would call the y component, but instead it's called the j component. So the other coordinate that we had, 5, 0, would be called 5 plus 0j. One more example here, I guess, I had forgotten about, but 7, 2, the coordinate 7, 2 up in quadrant 1 would be 7 plus 2j. Nothing to it. All right. Now what we're going to be doing today and tomorrow is we're going to work with some of the operations involved with vectors. And the first operation, the simplest operation, is called scalar multiplication. Think about it this way. If you were driving 60 miles per hour north and you doubled your speed, you'd be multiplying that vector by 2. What would you end up with? If you doubled your speed from going 60 miles per hour north, you'd be going 120 miles per hour north, right? Twice the speed, same direction. That's what scalar multiplication does. A little notation. First of all, the magnitude of a vector v, and again, the v is in bold because we're talking about a vector, is represented by, and we use something that looks like the absolute value signs. Or we simply take the lowercase equivalent. If we drop the bold, we're referring to just the magnitude of that vector. So for example, if we said the vector u is 12.0 at 81 degrees, like the example we had before, then we would say the magnitude of u is 12, and we use absolute values to represent that. Or we could just write lowercase u without the bold equals 12. Now if we take a positive scalar and multiply it by a vector, we change the magnitude but not the direction. Here's a couple of examples. You have these in front of you. First of all, let's define a vector v to be 3.0 at 55 degrees. Now if we take 2v, we're going to have a new vector. It's pictured there, but it'll be 6.0 at 55 degrees. Or if we take negative 2v, we'd take negative 2 times the original magnitude of 3.0, and we have negative 6.0 at 55 degrees. Or in other words, positive 6.0 at 235 degrees by adding 180 degrees. Idea makes sense? Okay, let's do an example. Let's say that u is equal to 15.8 at 55 degrees. We want to find 2.5u and negative 3.5u. Again, putting a little arrow over the letter indicates a vector because it's kind of hard to write bold unless you take the time to dull your pencil. 2.5u is going to be equal to, yep, 2.5 times the original magnitude, which was 15.8, and that's still at 55 degrees, which gives us the resultant of 39.5. At 55 degrees. Negative 3.5u is going to be negative 3.5 times 15.8 at 55 degrees. Negative 3.5 times 15.8 gives us negative 55.3 at 55 degrees. But here again, it's not wrong to use negative magnitudes, but we typically will write them with positive magnitudes. So we can write that as, yep, 55.3, and add 180 degrees to that. 235 degrees. That would be the preferred way to write it. And we're done. Scalar multiplication. Okay. Well, you can take two vectors, any two vectors. Today we're only going to focus on vectors that are perpendicular. Tomorrow we'll see how to do all the others. But you can take any two vectors and combine them to form a resultant vector, which has the same net effect as a component vector. For example, if a football team, if a running back runs and gets a 7-yard gain on the first down, the second down gets a 4-yard loss, those two plays have a net effect of a 3-yard gain. Okay, so you can take all these individual vectors, add them up, and you have a net vector. And you do that by placing the vector components tip to tail. So here's an example of this. Still the same. Okay, so we have 5.0 at 0 degrees. That's going to be off to the right 5 units. Then we've got another vector pointing off at 90 degrees, which is straight up with a magnitude of 7.0. 7.0 slightly longer. Now, what we have to do is we take and add them tip to tail. That is to say, again, we don't have to draw the vectors at standard position. That's just always going to be our starting point, or starting at the origin. We could take the blue one and move it so that its tail is at the tip of the red one, or we could take the red one and move it so that its tail is at the tip of the blue one. Let's take the red one and move it. So I'm going to bump it over here, put its tail at the tip of the blue one. The resultant will be the original starting point to the final ending point. That is the tail of the beginning, typically the origin, to the tip of the final vector. So that purple one is the resultant. You can think about this as, suppose you were driving north in your car, but there was a strong wind from the west. Okay, what net effect does it have, assuming you're on glare ice and lose control of the car? You're going to end up veering off to the right. Well, let's actually find out what the resultant is. Let's find the magnitude first. Magnitude, nothing to it, use Pythagorean theorem. So we know that our legs have magnitude 7 and 5. We'll call our resultant vector r. So the magnitude of r will be the square root of 5 squared plus 7 squared, which turns out to be square root of 74. So we know our magnitude now. And that's going to, we could convert that to a decimal, 8 point something, but we'll just leave it the way it is because that's exact. And the direction, well, the direction is just our angle reference to the x-axis. We've done all the trigonometry, so we're going to use tangent. The tangent of theta has got to be 7 over 5. And if you work that out, then theta is going to be inverse tangent which turns out to be, we'll typically work in degrees with vectors, though we wouldn't have to. 54.5 degrees. And so our resultant vector is the square root of 74 at an angle of 54.5 degrees. We found the resultant. We're done. Another example here. Number of questions in your book about this type of problem. We got two vectors, A and B. They're perpendicular. Magnitude of A is 15.9. The magnitude of B is 22.7. We want to find the magnitude of the resultant V. Now, it doesn't matter which one you put where, but to be careful, notice we want to know the angle between our resultant and B. All right? So which one, A or B, should we put on the x-axis? A or B? We should put B on the axis. Our resultant is going to point somewhere up here. And if we want to know the angle between our resultant and B, let's put B here. Otherwise, we're looking for the angle between our resultant and B if it were up here, and that's not the angle that we typically find. So we'll put B on the x-axis, only because this problem says between our resultant and vector B. So we're going to put B has a magnitude of 22.7. A is a little shorter. It has a magnitude of 15.9. Again, we don't have to draw them on the Cartesian plane as long as we draw them perpendicular. The resultant is going to be up there. From taking, this time I'm going to take vector B and move it so that it's, we move the horizontal one. We could move either one. We can move both if we wanted to, but now the magnitude of V is going to be the square root of 22.7 squared plus 15.9 squared. And the magnitude of our vector turns out to be, okay, 27.7 is our magnitude. Now, again, I just want to emphasize it's a minor point, but it could be a point of hang-up. Each question is different. Okay, these type of questions, it could say find the angle between the resultant and vector A. This one says B, so we're looking for this angle. If it said between V and A, we'd be looking for that angle. I didn't label it, but this was vector A. So here again, we can move one or both. Here's the angle we're looking for. It's always going to be tangent. If tangent wasn't your favorite trig function before, it will be now, because we use tangent for almost everything for the next few days. Tangent of theta is going to be 15.9 over 22.7, and our angle works out to be 35.0 degrees. And so the resultant vector, in this case we called it V. Well, then our vector V, we've got our magnitude of 27.7 and an angle of 35.0, and we're done. Okay. Resolving vectors does just the opposite. If we know the magnitude and direction of a vector V, we can break it into its horizontal and vertical components. And those are the components that lie along the x and y axis. So we do that, again, using trigonometry. First of all, let's just take this scenario. Let's take a vector V. Now, the x component is, of course, going to lie right along the x-axis. And we call that component, we just put a little subscript of x on there to show that that's the x component. It's still a vector. We'll often just deal with the magnitude of it, but it's still a vector. The y component would be along the y-axis. But so that we have a triangle, we're going to bump that over, just translate it so that it is tip to tail with v sub x. and we have our three vectors. Now, we've got an angle theta down here. First of all, let's take a look at the cosine of this vector. Excuse me, the cosine of theta. We know that the cosine of theta is going to be what over what? Vx, and I'm going to drop the arrow now because now I'm just talking about the length of it. Cosine is going to be Vx over V. All right? Well, if you multiply both sides by V, what do you end up with? If you multiply both sides by V on the right side, it cancels, and we're left with Vx. That's just the magnitude now, no arrow over the top. And on the left side, I multiply by V, and I get V times the cosine of theta. So there, we've got a formula. This will work regardless of the vector, regardless of the quadrant. If we want to know what the x component is, we just take V, the magnitude, times the cosine of the angle. What about sine? Sine of our angle theta is going to be Vy over V. Multiply both sides by V, and we find out that Vy, the y component, is always equal to the magnitude of V times the sine of theta. Now, I got to caution you about a wildly common error here. Be careful to associate the correct function with the correct component. If you want to find the x component, you always take the magnitude times the cosine, because the x always lies along the adjacent side. The y component is always the opposite side. And if we want to find the y component of a vector, we take the magnitude times the sine. The common error is your brain automatically thinks of x and y in that order, x, y. Your brain also automatically thinks of sine and cosine in that order, sine and cosine. But x is not associated with sine. A common error is to think x goes with sine, y goes with cosine. That's not true. So this is corny, but still to this day, this is how I keep the two straight, and it's still what I think of every time I work with them. Y and sine rhyme. Okay? If it works, it works. So you want to find the y component, we're going to take v times the sine of theta. So let's do an example here. We've got a vector A that's equal to 615 at 165 degrees. Find the x and y components. We don't need a picture anymore. These two formulas always take it right through us. If we want to find the x component of A, we just take the magnitude of A, which is 615 times the x component, so we multiply it by cosine of 165 degrees. And so our x component to that vector turns out to be negative 594. Now just think about that. Your x component is negative. Does that make sense? Where does the vector 165 point off to? Quadrant 2. It's pointing off to the northwest. All right? Top left. So it should be pointing off to the left. And it is by the negative sign. The y component is going to be 615 times the sine of 165 degrees. Now it's pointing off to the second quadrant. That means it's pointing slightly upward, which means this ought to be positive, and it is. AY, that is the y component of A, turns out to be 159. And we're done. That's all there is to it. 2 quick steps, and we've got it converted. Or we found the components, I should say. All right. Well, going back to resolving vectors here, we can now find the resultant of 2 components according to what we did before. We're just going to state these 2 facts because we already summarized this a little bit. If we want to find the magnitude of a vector and we know the x and y components, we just use the Pythagorean theorem. The magnitude has got to be the x component squared plus the y component squared. Take the square root. We'll do that in just a minute. And we also know that the tangent of our direction has got to be the y component over the x component. Now you need to be careful here because sometimes your vector will point into the third or fourth quadrant, but when you ask your calculator won't always give you the right angle. If your vector is pointing off down here, your calculator will never tell you that. Your calculator always gives you an arctangent angle that is up here. We'll see an example of that in just a minute, but you have to be mindful to always make sure that we're putting the correct angle on our vector. So, let's take a look at an example right now. We don't know what the vector is here, but we do know what the x and y components are. We're doing the opposite of what we just did. We know that the x component is negative 23.74. And the y component is 9.22. Now, it's a simple question, but always ask yourself, what quadrant is this vector in? It's pointing off in quadrant 2, somewhere back there. So our angle is going to be somewhere between 90 and 180 degrees. Okay? All right, well, we can find the magnitude of v. Again, we don't need bold for the magnitude. The magnitude squared is going to be equal to the x component squared plus the y component squared. And again, I'm not drawing a detailed picture because you want to wean yourself off of that. You can do all this work with vectors without the picture. So our magnitude is 25.47. Now, should I have a little arrow over this or not? Nope. It's not a vector. That's just the magnitude. So we just write v. Okay, we got half of our answer. What about our angle theta? We know that that angle theta is going to be somewhere over here. And we know that the tangent of theta is going to be the y component over the x component. In this case, 9.22 over negative 23.74. Now, if you do this on your calculator, it's not going to give you the right answer. Andrew, what did you get for an angle theta here? Yeah, your calculator only gives you one of more than one possible solution. So it actually gave you that. It's right, tangent is negative. It gave you the one down here, but the other quadrant where tangent is negative is the one where our answer is, and that's quadrant 2. So the quick way to get your angle is add 180 degrees to that, and it turns out to be 158.8. And so then we can conclude that the vector, our resultant, vector v, now I will put the arrow because we're going to list the whole vector, it's equal to 25.47 at an angle of 158.8 degrees. And we're done. We found the resultant based on the x and y components. Questions up to this point? Nothing? All right. Well, the last thing we have to do, we've already done all the math for, we just haven't called it this. Let's write the vector 23.5 at 207 degrees in rectangular and complex forms. Writing a vector in rectangular form is the same question as find the x and y components. So, for this vector, the x component will be 23.5 times the cosine of 207 degrees. That'll tell us our x-coordinate of the tip. The y-coordinate will be given by 23.5 times the sine of 207 degrees. Now here again, the x component and y components were both negative. Where's the quadrant where that occurs? It's going to be somewhere down there in the third quadrant. Does that agree with the angle we were given? Yeah, 207 degrees. Okay, so it's consistent. So our tip is located at negative 20.9, negative 10.7. There it is. We're done with rectangular form. What about complex form? No math to do. Negative 20.9 minus 10.7j. We're done. Rectangular and complex forms. Go right. And the last one of the day. Let's take this vector 5.25 minus 3.47j and put it in rectangular and polar forms. Well, let's go to rectangular. (5.25) negative 3.47. That's done. What quadrant is this vector lying in, or pointing towards, I should say? Fourth quadrant. Don't need a sketch, but there it is. And the tip is located at 5.25, negative 3.47. Sketch isn't necessary, but those are just the two legs of your right triangle, so we can find the magnitude. We'll call the vector v here just to give it some name. Magnitude will be Anybody work out that magnitude? And now we got to work out our angle theta. We know the tangent of our angle is always the y component over the x component, which is negative 3.47, 5.25. What about an angle? The tangent of theta is going to be negative 3.47 over 5.25. Probably your calculator says that it's negative 25.2. Oh, I used 2.27 again. Yeah, my angle's going to be wrong too. Good. What does it tell you for this angle? Negative 33.5 degrees, which is true, but we tend to like to express the angles as positive values, so we can spin that around by adding 360 degrees to it. And we get an angle of 326.5 degrees. And we're done. The polar form of this vector, we really don't need to name it, is 6.29 at 326.5 degrees. Polar form, rectangular form, complex form. And we're done.